we consider a simple object. It has full axis, so it's the center of mass right in the middle. And it has x, y, and then 90 degrees to x and y, so across x plus y, with the right hand being z. So the solution is given by x, y, z. Write this down. What we will do is throw this object in there, and then we try and see how the object will go. And here, if it is set, the solution is this relation to state C, yes, we can learn. So the question is initial condition, orientation, and linear angular velocity. So we need to the equations into a simulation that will use ODE and then do the animation. Sets of deriving equations. So this will be then Euler Lagrange equations. The second one is we need to compute the position and orientation of the object. So the position orientation is just one x, y, z. The orientation given choice is any of the combination between orientation to 1, 3, 1. Whatever other angles for these, let's say other angles. Other angles, it's 3 to 1. Relations z, y, x, c, y, x. And what's what we do is psi rotation over z, theta is the rotation over y, and phi is the rotation over x. Okay, last one is definition of the linear and angular.
Hey, is it better now? Can you hear me? The audio? Okay, I think I know what the problem was. Okay, so let me just recap. We are trying to do 3D dynamics of a three-dimensional object. So the question is, given initial position, orientation, and linear angular velocity, that is the initial, of course, we need to describe the motion of the object. We need to write the equations. We need to create a simulation, which we'll do using ODE, and then animation. So the first part is to compute the equations of motion, which we'll be doing using Euler-Lagrange equations. So step one. So position orientation is known. It's x, y, z. The Euler angles are, well, we'll use 3 to 1, but you could use any of the one of the 12 ones available, 1 to 3, 1 to 1, and so on. We need to compute the linear angular velocity. The linear part is easy. It's just x dot, y dot, z dot. No problem. The angular velocity, well, there were two things we had done. We had done angular velocity in world frame. This would be omega x, omega y, omega z, and that angular velocity will always be along the global xyz. But we also looked at omega in body frame. This angular velocity was omega bx omega bx omega by, omega bz. Okay, and let me not write those expressions down, but I need to write omega as a function of the Euler angles, right? Omega or omega b as a function of Euler angles, phi dot theta dot psi dot phi theta psi. So I'm not writing it down because right now I'm not sure which angular velocity to use. Okay, so I'll just keep from writing it, but I'll write it down a little bit later. But we have formulas for both of those in terms of the Euler angles and Euler angular rates, Euler angles, Euler angular rates. Okay, next step is to compute the kinetic energy T. That would be half m x dot square y dot square plus c dot square plus half omega transpose I omega. Okay, why did I write this like this? Well, omega is 3 cross 1. Omega transpose is 1 cross 3. Inertia matrix. Now we are talking about inertia of a 3D object, and that inertia matrix is going to be 3 cross 3. It's going to have Ixx, Ixy, Ixz, Iyx, Iyy, Iyz, Izx, Izy, Izz. Okay, and this angular velocity is in the world frame, omega x, omega y, omega z. Okay, now here's the thing. Omega x, omega y, omega z is in the world frame. So when the object is turning, that angular velocity is basically going to be fixed to, let's see, this is the fixed frame, x, y, z, world frame. And then the object itself is going to be turning. So x, y, z. Okay, so this thing here is the world frame angular velocity. Okay, and then I is going to also be in the world frame. Okay, so as the object rotates, okay, so as the object rotates, the world frame velocity will change with time. Right, because the object is actually rotating and its angular velocity in the world frame will keep changing. So it's a lot of work to keep track of the angular velocity as the object rotates. There will be a rotation matrix involved and you transform. If you look at textbooks, or manuals which list the angular velocity, they'll always list the angular velocity in body frame. So this give inertia in the body frame. Okay, in fact, for an object like this, you will see that inertia could be as simple as IB x 0 0 0 I B y 0 0 0 I B z. So it's a nice diagonal form. Okay, not all of them would have this inertia, but many times you'll see the inertia is nice this form, and this is constant, does not change with time. Okay, while this one, the world frame one, does change with time because the object is rotating. So clearly we are better off using this one rather than using this one, which is really complicated to compute. So what we can do here is it can actually be shown that omega transpose I omega, which is basically the rotational energy associated with turning, is the same no matter what coordinate frame you use. So you could just do this in body frame. Okay, it doesn't really matter which frame you use. So we are inclined to use, we should use this one and not this one, because this is complex while this is simple. So we'll actually use omega b here and not use omega in the world frame. So what we can do is we can, now that we have this, we can write omega b for our angular velocity and not world frame velocity. So we know that relation between omega b and phi dot, theta dot, psi dot. I'll write it down in just a bit. Okay, so what we know is omega b omega bx, omega by, omega bz equals 1, 0 minus sine theta 0 cosine phi cos theta sine phi 0 minus sine phi cos theta cos phi, followed by the Euler angles, so Euler angular rate phi dot theta dot psi dot. So we'll use this in this form. So now we can write t as half m x dot square plus y dot square plus z dot square plus half omega b transpose I b omega b. And this could actually be as simple as, let's see, x dot square plus y dot square plus z dot square plus half what did I write for this? IBX, okay. IBX omega b x square IBY omega by square plus IBZ omega bz square. So it's much simpler than that complicated one with world frame. Now, what you could do also is, well, you also need to do is you need to sub this in, right? This value comes from here, this row, and so on. So this will be, all of these have to be written as functions of theta, phi, psi, theta dot, phi dot, psi dot from this expression. And that's too complicated. I'm not going to try to do that, but I'll do it in code. So I'll substitute that in code so I don't have to worry about this. Next is V, the potential energy. It's simply mgz. And then the L is T minus V. So half, it's all we already got T and got V, so we can sub that in. And finally, the third part is equations of motion. Okay, so for that, this is very standard of what we have done. Here we have the equations come as follows: d dt dl dq dot j minus dl dq j equals qj. Here q j would be x, y, z, phi, theta, psi, and all the qj's, which are basically the external forces, will be 0. So no external forces. Okay. Once we get the equations, we can write ax equals b where x would be x double dot, y double dot, z double dot. So this is capital X. Theta double dot, phi double dot, theta double dot, psi double dot, and then you can just integrate the equations. Once you get acceleration, you need to integrate acceleration once to get velocities, and integrate it once more to get the positions. So it's something we've done in the past. So that's the whole process. So I'll show you some code which will do all these things, but clearly it was important to write it down, otherwise it's very difficult to code it. Was similar to the previous files. I have a file which derived the equations of motion. It's very self-explanatory. I hope you basically go through the same steps. So position and angles. This is just following the notes. Angular velocity and energy. Okay, so TVL derive equations. You probably don't need to. You can just copy paste my code and get it to work for a different problem. I developed this code in the previous few lectures. And then you get A and B. A and B are needed for my ODE. So run this. So it just gives you a bunch of things which needs to be copy pasted in a falling block, which is okay. So parameters, but the equations should be buried in. Okay, so that's the A matrix came from the equations from here. You can see this A, the same thing was pasted here. Then there should be a B somewhere. B is here. Okay, and then A inverse B, pretty much the same thing, X, which we've done for two-dimensional problems. So running this shows the animation. This is the falling block. You can see that it's rotating. And it was rotating only because I provided with the initial angular velocity as well as a velocity in the upward direction. So all that is the initial condition is right. Not here, sorry. Okay, so these are the initial conditions. So I set some vertical velocity here, 5. Then I gave it some spin, 3 minus 4, 5, and that's why you see it's rotating.